Спасибо за приглашение посетить Санкт-Петербургский государственный университет. Я жил в этом городе в июле 1986, и многое изменилось.
As a student?
Я, когда студент. Позвольте мне говорить по-английски, потому что мои словарь и грамматика очень плохи, и я все забыл. Okay.
Ну, не все.
Почти все. So, I want to say a little bit about Fourier analysis, a little bit about number theory, and then finally a little bit about P-Adic groups. So I've been asked the following question several times in my career. What is the deal with the Fourier transform? On the one hand, it seems to be this machine for expressing periodic functions as sums of sinusoids. And on the other hand, it's this machine that, given a non-periodic function on the real line, gives you some other function that tells you something about your original function. Are these, and these two gadgets are defined by pretty much similar or the same formula. Are they just two things that happen to be analogous to each other, or are they special cases of one general thing? So I want to start by answering that question. So to start with Fourier analysis, here's the setting. So G is going to be a topological group. And so that means it's a group, it's got a topology, and the group structure and the topology are compatible. And for me, it's going to be locally compact and Hausdorff. And for the first part of the talk, let's just assume that our group is abelian. So examples, we got, well, here's an example that's going to be very important in this talk. So I'm going to consider this group that I'm calling T. So it's going to be the set of all complex numbers of absolute value 1. But of course, the real line, the multiplicative group of non-zero real numbers, finite abelian groups, etc. Lots of examples out there. Well, a non-example would be the rational numbers. It's not locally compact. So definition. A character, well, some people call it a unitary character. I'm going to leave out the word unitary, usually. A unitary character of G is a continuous homomorphism from G to this particular group T. It's over here. And the Pontryagin dual of G is, well, the notation is going to be G hat, and it's just going to be the set of all characters of G. So I can write down a couple of examples. What this means in practice. So for a couple of examples of groups G, I'll write down what a typical character looks like, and thereby we'll see what the Pontryagin dual G hat is going to be. So if G is the group T, well, a typical character of T is just a map of the form an element T goes to t to the n, where n is an integer. So we can identify g hat with the set of integers. On the other hand, if we take the group of integers, a typical character has the form. It's going to take an integer n to t to the n, where t is a particular element of capital T. And so we can identify g hat with t. And then finally, if we look at the real line, so a typical character looks like this. It's going to take a real number x to e to the I x y, where y is some fixed real number. So we can identify g hat with the set of real numbers. And so as you'll see from this chart, what's happening here is not very random. Lots of patterns here. Let me write down a few facts. About g hat in general. So, number one, g hat turns out to be a group. The operation is pointwise multiplication of functions. G hat has a natural topology. Since it is a collection of functions, the natural topology would be the so-called compact open topology. And these two structures are compatible, so G hat is a topological group. So you start with a topological group, its Pontryagin dual is another topological group. Well, more things that you can see illustrated, at least on this chart. If G is compact, then G hat is discrete. If G is discrete, then G hat is compact. And then finally, what I'm going to call Pontryagin duality. So let's suppose we take an element of a group G. Then let's consider evaluation at G, which is defined as follows. So to map from G hat to T. So eval at G evaluated at a character, which is to say an element of G hat, is going to be chi of G. So the map that sends G to eval of G is a map from the group G to the set of characters of G hat, which is to say G hat hat and theorem this is an isomorphism. So the map that I've written down is formally pretty much the same as the map you would use to show that a finite dimensional vector space is isomorphic to its double dual. However, in this particular situation, the proof of surjectivity is considerably harder. Now, in order to do some analysis, we have to have a measure on our group G. And there's a natural choice of measure. We're interested in a measure that respects the structure of the group. So if you have a subset of the group and you translate it around by by multiplying by some group element. We want the measure to not change. So this would be analogous to Lebesgue measure on the real line. You take a subset of the real line, you translate it around, and its measure does not change. So it turns out that, so this is called a Haar measure, and there's a theorem that says that groups of this kind do have Haar measures, and the Haar measure is unique up to positive scalar multiple. So that says that, well, up to positive scalar multiple, we have a natural choice of measure, and that means we can talk about LP spaces on the group G, and these spaces don't depend on the choice of measure. So there is a way to do analysis on these groups. Well, let me do some analysis. So so the Fourier transform of a function f in L1 of G with respect to our Haar measure is the function f hat on G hat given by the following formula. So f hat, since it's a function on G hat, I should be evaluating it on a character. So here, chi is going to be an element of G hat, which is to say a character of G. And this is going to be, f hat of chi is going to be the integral over G with respect to our Haar measure of f of little g, chi of G, complex conjugate. So what does this mean in a concrete case? Well, let's suppose that we're looking at the case where our group G is the group capital T. So if F belongs to 1 of T, and suppose I take a particular element of T hat. So what does an element of T hat look like? It's something that takes little t to t to the n. That's going to be an element of T hat. Then f hat of this character, which I'm just going to identify with the number n, is just this formula, integral over t, f of t, t to the minus n dt. Now, this doesn't look familiar necessarily, but let's suppose we do a change of variables. So instead of thinking of f as a function on the circle group, we could think of f as a nice function that on the real line that's periodic. Then we have f hat of n is going to be 1 over 2 pi. I'm normalizing the measure somehow. Integral from 0 to 2 pi of f of x e to the minus I n x dx. So this is just the nth Fourier coefficient. So this whole general setting does lead to something very familiar in the case of periodic functions. Another example, if we let f be a function on the real line, then this Fourier transform f hat of y is going to be integral from minus infinity to infinity f of x e to the minus I xy dx. So we recover the usual Fourier transform as well as the taking of nth Fourier coefficients from the general setup. Now, part of the usefulness of the Fourier transform of a function is that you can use it to reconstruct your original function. And that works in this level of generality as well. So, theorem Fourier inversion. So I guess the first part of the theorem I don't really want to state. It says that if your function f is nice enough, so a bit better than being an L1, then f hat is also an L1. So let's just take that as a given. So we can normalize the measure on G hat so that for all nice f in L1 of G, and I'm not saying just how nice is nice, f of G is going to be integral over G hat, f hat of chi against chi of G, dg, and I guess this is, d chi, that's almost everywhere. So if we look at what this is saying in the case of functions on capital T, it's saying that a nice enough function is the sum of its Fourier series. And we have a similar interpretation in terms of functions on the real line. There's only one more theorem I want to state about Fourier analysis in this level of generality. Let's consider the Fourier transform, and I want to restrict it from L1 of G to, let's say, L1 of G intersect L2 of G. Well, this extends uniquely to give an isometry from L2 of G to L2 of G hat. So in some sense, these two objects are the same. So putting this all together, there is a nice general theory that includes as special cases the Fourier transform, Fourier series, also other things, Gauss sums, stuff like that. What if G is not assumed abelian? Well, lots of things fail. The first thing is that it's not enough just to deal with characters. One has to deal with more complicated objects. And so I want to define a representation of G is a pair pi comma v, where V is a vector space over C, and pi is a continuous homomorphism from G into the group of invertible linear operators on V. And we might, V could be infinite dimensional, and so we might care about operators that have particular properties. I'm not gonna worry about that. So example, you could take G equals GLN of C. We could take V equals C to the N, and then we could take pi from G to GLV, the identity. Another example would be we could take V equals L2 of G, then G acts on V by translation. Okay, so I've defined the general notion of representation. It's basically a group acting on a vector space. And I should also say that a representation is irreducible if the vector space has no closed proper invariant subspaces. So looking at the two examples that I gave here, first example is clearly irreducible, but if we look at G acting on L2 of G, that's highly reducible. And that particular representation is a subject of a lot of interest. So, well, why are representations the right, a reasonable generalization of characters from the abelian case? Well, so here's a fact. If G is abelian, then all irreducible representations of G are one-dimensional. And in particular, unitary representations, and I haven't defined what that means. They are characters. So I'm going to give a definition of G hat in the non-abelian case. And because of these facts, this boils down to my previous definition if G happens to be abelian. So let's define G hat to be the set of irreducible unitary representations of G. This is a somewhat different object than in the special case of G being abelian. So here are some facts. First of all, G hat still comes with a natural topology and a measure.
V is Hilbert space.
Could be.
No, first of all, you define topology in V. Because you can't say about closed subspace.
Oh, sure. So, okay, take Hilbert spaces. I mean, so later on I'm going to be working in a different category of representations that works on a different kind of space. But yeah, classically this would be Hilbert space. Yeah. G hat still has a topology and a measure. G hat is generally not a group. The structure of G hat could be very complicated. So, for example, if G is a Lie group, then G hat could be, say, a union of complex manifolds of different dimensions, where the manifolds might have a non-Hausdorff topology on them, and then there's other complications that come in as well. So, yeah, it's got a structure, but it can be pretty complicated. In this setting, we do have, nonetheless, analogs of the Fourier transform, and Fourier inversion, and so forth. But they're a lot more complicated because one has to deal with these representations, and these representations are not functions on the group, but if things work out rightly, then you can sort of replace the representations by certain functions called characters, and you can kind of get things to work. There's a nice theory of representations that, well, I guess one of the early facts, I should say, is that if G is compact, then G hat is discrete, just as before. And this, I guess, boils down to the Peter-Weil theorem. So there's a sense in which the theory for compact groups is pretty satisfactory. Non-compact groups are much harder to deal with, but there is a good theory for non-compact groups that, particularly for Lie groups, GLN, SLN, symplectic, orthogonal, unitary groups, exceptional groups, E7, E8, for those of you who were in the room before. There are some Lie groups that correspond to that. And so there's a nice theory that kind of encapsulates them all. And some of the early figures were Harishchandra, Gelfand Naimark, well, lots of people. It's been a big industry, and it continues to the present day. So now I'd like to pretend to change the subject completely. Let's suppose you have a polynomial equation and you want to find integer solutions. Okay, so here's a polynomial equation that's generated a modest amount of interest over the years. But that one's a bit hard because it has 3 variables. Let's deal with an easier one. Okay, so let's suppose we're trying to figure out if an equation like this has a solution in integers. Well, in general, if you have a solution in integers, then that's going to give you a solution in the real numbers. And that's pretty helpful here because we can use methods of calculus and determine that there is no solution in the real numbers, therefore there is no solution in the integers. That's one way to do it. On the other hand, not all equations are going to be this easy. Well, if you have a solution in integers, what else do you get? Well, you also get solutions mod m for all natural numbers m. And not just that you get randomly scattered solutions, but for each m you get a solution, and these solutions somehow form a coherent system. And well, by the Chinese remainder theorem, having a solution mod m is equivalent to having solutions mod the prime powers that divide m. So this is equivalent to having solutions mod p to the r for all primes p, all r greater than 0. So this is something you're going to have if there's a solution in the integers. And so if you fail to have a solution in R, then you fail to have a solution in the integers. If you fail to have any of these things, you fail to have a solution in the integers. Well, what would a coherent system of solutions to an equation look like? Well, let's do this one prime at a time. Let's fix p equals 5. And let's consider the equation x squared plus 1 equals 0. So what does a coherent system of solutions look like? Well, let's consider the group of integers mod 5. And let's also consider the group of integers mod 5 squared. We have a map, reduction mod 5, from one group to another. Let's consider the group of integers mod 5 cubed. We have a reduction map, reduction mod 5 squared. And then finally, integers mod 5 to the 4. Okay, and then this continues. So here's a solution mod 5. 2 is a solution for this equation. And we have a solution mod 25, not just any old solution, but a solution that actually reduces mod 5 to give our solution number 2. So 7. And how do I know that 7 reduces to give 2? Because 7 is actually 2 plus some multiple of 5. Meanwhile, mod 125, I've got 57. And I know that reduces to 7 because I can write 57 as the previous number plus some multiple of 25. And then I've got 187. And I know 187 reduces to 57 because I can write this as 2 plus 1 times 5 plus 2 times 5 squared plus 1 times 5 cubed. So there's a theorem known as Hensel's lemma that says, in fact, we can continue this process indefinitely, though I'm not going to. That's not what's important for me. We also could have started with 3 here, and we get a totally different system here. Now, so this notation for a coherent system of solutions is really cumbersome, and we'd like to have a
182.
Yeah. I did that deliberately just to see if you notice. Right? The idea is the important thing. So here's a better notation. Than the diagram above. So let's just start with 2 plus 1 times 5 plus 2 times 5 squared plus 1 times 5 cubed. And then just in case you think you notice a pattern here, 3 times 5 to the 4th plus, and let's just say this continues. So what I've written is a power series in 5. In general, a system of solutions looks like this. So I'm going to have a coefficient a0 plus a1 times p plus a2 times p squared plus etc., where each of the coefficients is going to be greater than or equal to 0 and less than p. Well, okay, this is highly divergent, but there's 2 ways to deal with this. One is to say, well, don't worry about it because this is an object, and you can figure out what's the right way to add 2 such objects or multiply 2 such objects. So it's perfectly okay. Another way to deal with this is to change the topology So you get a new topology where things do converge. I'm not going to be talking too much about the topological properties of this object. In fact, one could give a different introduction to P-Adic numbers that really focuses on the topology, and it would look almost disjoint from what I'm saying. But it's in fact exactly the same thing. Let me write down a few properties of the collection of these power series. I'm going to give it a name. Let's say Z sub p is the set of all of such power series in P. And Q sub p is going to be the field of fractions of the set of power series, which is to say the set of Laurent series. So we call Z sub p the P-Adic integers, and we might call Q sub p the P-Adic numbers. So here are some properties. Of QP. So it's like the real line in some ways, but it's also like the rational numbers in some other ways. So like R, QP is a locally compact field. Not only that, it's you can think of the real line as being a completion of the rationals with respect to the absolute value function. Well, QP is also the completion of the rationals, but with respect to a different absolute value function. So a different function. One could introduce the P-Adic numbers by simply defining this function, this new absolute value function on Q, and saying, well, take the completion. And you'll get the same thing. And that'll be a more topological point of view. Well, because QP has these properties, it's a domain where you can do calculus. And it's fair to ask if you're a college student, an undergraduate, if you were to do calculus using, say, P-Adic functions on a P-Adic field, instead of real functions on the real line, what of the theorems that you know remain true? I think some of them remain true. Sometimes the opposite of what you expect is true. And sometimes it's somewhere in the middle. So it's a nice test bed to see how well do you understand what's going on with real calculus. Well, I said that the P-Adic numbers has some properties in common with Q. Well, like Q, QP has lots of finite dimensional field extensions. So in other words, there's a rich arithmetic. That makes QP more like the rationals, less like the reals. In the reals, there's not much to say about whether a polynomial has real solutions or not. That's not a very hard question. If it has rational solutions or not, that can be hard. So there's more going on in terms of arithmetic if you're dealing with QP. Now, so to return to this picture here, we can say that if an equation has a rational solution, then it has a solution in R and in QP for all P. A solution in Q implies solutions in R and QP for all P. That means if you have some polynomial and you want to know if it has a solution in Q, if it fails to have a solution in R or QP for any P, then you know it fails to have a rational solution. And because you can do calculus in R and you can do calculus in QP, there's methods that are available for you. Now, one could ask, is the converse of this true? And the answer is no. And that's why Hensel did not prove Fermat's last theorem back in the 1890s. However, there are some celebrated problems over Q that can be solved by solving the analogous problems over R and QP. So for example, let's say you want to classify the quadratic forms over the rationals. That's a very hard problem. It's not hard to classify them over the real numbers. For similar reasons, it's not hard to classify them over the P-Adic numbers. The classification is very different, but you have the methods of analysis available to you, and so it can be done. And so we can reduce and it turns out the two bilinear forms, two quadratic forms are equivalent over Q if and only if they are equivalent over the reals and the P-Adics for all P. So this allows us to take a hard problem and reduce it to an infinite number of easy problems, which is better than it sounds. Okay? I do want to mention one weird property of this absolute value function, this function that I've not defined for you at all. So let's recall the triangle inequality, which says, among other things, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Well, in QP, we have a different absolute value function, and it satisfies a better property. Absolute value of x plus y is less than or equal to the maximum of the absolute value of x and the absolute value of y. It follows very easily from the definition of the absolute value, which I have not written down, but it's still a bit hard to believe. It's hard to visualize what this means. Here's a consequence. In QP, let's suppose you have a sum of an infinite series of P-Adic numbers, and you'd like to know, when does this converge? Well, this converges if and only if the terms go to 0. Okay? So, something that calculus students already know. Okay? But in P-Adic numbers, it's actually true. So certain aspects of P-Adic calculus become much easier than what you would expect. Okay, well, I haven't said anything yet about P-Adic groups. So P-Adic groups are built out of the P-Adic numbers in the same way that Lie groups are built out of the real numbers. So, for example, you've got GLN of QP. So there's the group of invertible n by n matrices with entries in QP. You can take the matrices with determinant 1. Then you have so-called classical groups. symplectic, orthogonal, unitary groups. You've got exceptional groups. So for example, there's a P-Adic E7, for those of you who were in the previous seminar, etc.
These are algebraic. You're speaking about P-Adic analytic groups? Or?
Well, so what I'm saying is let's take an algebraic group like GLN and plug in, take the rational points with respect to a P-Adic field. Okay. And not all of these are going to be definable over the integers or the rationals like these are. There's going to be others as well, but certainly all of the the reductive Lie algebras, G2, F4, all those are going to lead to P-Adic groups. And there's others that come from the fact that we have this rich arithmetic of field extensions of QP. So some of the early figures in the study of these groups overlap a lot with some of the early figures in the study of Lie groups. So again, there's Harishchandra. Again, there's Gelfand. There's Kazhdan. There's Piatetsky-Shapiro. There's Bernstein. There's Howe. It's been, a lot of people have worked in this area. Now, Harishchandra has something he calls the Lefschetz principle. It's not a very precise statement, but he says whatever is true for real groups is true for P-Adic groups. Now, this statement by Harishchandra is, on its face, completely absurd. The groups do not look the same at all. If you start writing down representations, you get collections of representations that look very different. If you try to do analysis on these groups, things don't seem to work out the same at all. In fact, even the kind of vector space that you should be using isn't the same between the real case and the P-Adic case. In the real case, as you point out, we should generally be using Hilbert space. But in the P-Adic case, it turns out to be more convenient to use certain complex vector spaces on which we put really no topology at all. Okay, so we have this absurd statement, but maybe it's true on some deeper level. So there's a conjecture that says in what sense this is true. And it also illustrates a motivation for this whole subject. So I want to give a compact statement of local class field theory, and here's why. So one could say that arithmetic is an understanding all finite dimensional extensions of Q. In Russian, do you have the notion of scare quotes? Is it?
Yeah.
Scare quotes. Okay. So, so in America, if you see a sign that says "Свежная рыба," then you have a sense of what it means. But if there's quotes, if it says "Свежная рыба," then you have your doubts. Okay? The quotes could mean so-called, or I'm saying this, not that it's necessarily true. Okay? So, sort of. Arithmetic is understanding of all finite extensions of Q. Well, this is a really, really hard problem, but easier sub-problem. Let's instead let's concentrate on the so-called abelian extensions, and let's instead look at QP. And that's what local class field theory tells you. So here's a compact statement of local class field theory. I should say let F is going to be real, complex, or P-Adic, or lots of other things that are related. So if F is any of these fields, you take the so-called Weil group of F, which is related to the absolute Galois group. You take its abelianization, and this is an isomorphism. There's a natural map that's an isomorphism. And so this...
What is LCFT?
Oh, sorry. Local class field theory. Yes. I've gone a bit overboard with the abbreviations here. So here's an equivalence statement. To say that two things are isomorphic is to say that their maps into the non-zero complex numbers are isomorphic. So let's consider Hom from the Weil group. I don't need to worry about the abelianization because that's not going to be seen here. That corresponds with Hom F cross into C cross. Okay? Here's another statement that's equivalent. We'll look at Homs from the Weil group to GL1 of C. Those correspond to, well, these are irreducible representations of GL1 of F.
Complex.
Yes, complex representations. So far, everything I've had to say is about complex representations. I may say about 30 seconds about other representations. So this is a nice compact description of local class field theory, partly compact because I've left out all the details. Here are some conjectured generalizations. Due to Langlands. So first of all, he says, you see two copies of GL1 in that last statement. Let's replace GL1 by GLN. And then, well, at the cost of extra complexity, let's replace GLN with a more or less arbitrary reductive group that could be P-Adic or real or complex. We're treating them in a uniform way. So replace GL1 by a reductive group G. And what you get is a slightly more complicated statement. So we're going to have admissible, I'm not going to say what that means, maps from, I'm going to take the Weil group, I'm going to make it a little bit more complicated. I'm going to go into a complex group that's related to G in a certain way, the so-called Langland's dual. And I'm going to add a little bit of extra information. These correspond one-to-one with irreducible, admissible, I'm not going to worry about what that means, reps of G of F. So here we have a statement that's uniform for real groups, complex groups, P-Adic groups, and some other groups as well, and that tells you, it gives you parameterization of the representations. So we started with local class field theory, which was about abelian extensions. If you understand this, then you understand something about non-abelian extensions. So you know more about arithmetic than you did before. Now, so what are the developments? So GL2 has been done by Kutzko. GLN was done in 1999 by Harrison Taylor and NER. It's been reformulated. There's been a streamlined proof by Peter Schulze around 2015. I would say that classical groups are pretty much done due to James Arthur, and there's other groups here and there that have been handled. One can expand this subject in many ways. One can deal with non-complex representations. There's a theory of so-called L-adic representations, P-adic representations, representations over the algebraic closure of a finite field. In each of these cases, there is a conjectured correspondence like this, and there are some theorems that say that in certain cases the correspondence works. So that's one expansion, non-complex. Another expansion is the so-called geometric Langland's program that might have been the subject of last week's colloquium, where you replace your P-adic fields with certain function fields, and you use more methods of algebraic geometry. There's higher dimensional class field theory. I think Parshin may have started that up. And then there's also the so-called relative Langland's correspondence, which I think Dipendra may have initiated, though that's in its infancy like many of these things. So this subject is expanding in many directions, but whether or not you are interested in those particular expansions, you could care about those expansions, or you could just deal with this classical problem. Either way, it turns out that this subject, it connects number theory, harmonic analysis, and algebraic geometry in a pretty nice way, and it's got no shortage of interesting problems. So I'll stop there.
It's done for this case. It's approved.
Yes, these cases are done.
Yeah, okay. So for example, for symplectic is not known.
So symplectic, it is. So it.
What do you mean by classical groups first?
Oh, sorry.
Yeah.
So by classical groups, I mean, well, right, because different people define this word differently, and so the groups that Jim Arthur actually dealt with are symplectic and orthogonal groups. One of his students finished up the case of quasi-split unitary groups. I believe the non-quasi-split case has been done. And that's what I mean by classical groups.
Excuse me once again, so only split and quasi-split groups?
That's a good question. So have the non-quasi-split groups been handled?
Orthogonal, usually that's the first thing you look at.
So I think actually, so definitely the quasi-split orthogonal groups. Have the non-quasi-split ones been done? I'm not positive. Probably the so-called pure inner forms, which is a bit technical, but means a bunch of other orthogonal groups have definitely been done.
So for what group is open? The problems.
Oh, well, so I think it's not known for exceptional groups. It might be known for spin groups in small rank. There is not, say, a nice uniform proof that doesn't take in too much information about the specific group into account. So, in a certain sense, the groups that you're most likely to encounter have now been dealt with, but in another sense, most groups we still don't know.
So what you mentioned are Chevalier groups and twisted forms, yes?
So we got some
classical Chevalier groups and twisted
yes.
forms. And complex case, or
Complex. So the real and the complex cases were. I should have mentioned that they were done. They were already done. I think in great generally.
Complex representations.
Oh, complex. Yes, right. And here I'm only talking about complex representations. Again, there are people who work in L-adic representations.
For a different for a different prime.
For a different prime, and there's other people who work with the same prime, and so you have very, very different methods. It's a totally different situation when you have the same prime.
Yeah, a more simple question. If you take all this theory P tends to infinity, will you get as limiting case something like C or something?
That's a good question. So, in terms of notation, yes, because sometimes people write Q sub infinity equals R, but that's just a notational question. Does it make sense to ask what happens when P goes to infinity? I'm not sure if it makes sense. I'll think about that. That's not funny.
Can I just make a remark about this question? This question is really how you go to infinity. If in the usual sense it's not true, because you know what is the limit on spec of Z. But in some strange senses like Durof's, you know about Durof's thesis about some generalization of spec Z and its completion, then in some sense you could take limits, but it's, you know.
I mean, there ought to be some reason why things are working out in the same way.
Yeah.
Right. So I know that, say, in the geometric Langlands picture, they think of the number theory situation as some sort of something that follows in some residual way from a bigger story involving quantum groups.
Mm-hmm. Technically admissible here replaces continuity or something.
Yeah, admissible is a little bit better than continuity. So and admissible means something different whether you're looking at real versus.
You cannot make it continuous in the usual sense because the topologies are different. So.
I mean, you can, but it's right. Admissible is a nice condition. It's saying, I guess in the real case, admissible means that when you restrict to a compact subgroup and you decompose into irreducibles, you have finite multiplicities. Well, admissible is formulated differently in the P-Adic case, but it does boil down to kind of the same thing there.
Mm-hmm.
Okay, so let's thank the speaker again.